Welcome to this repeat class of biochemical basis of cancer treatment, and we will be refreshing your memory about various factors that pave a future for all of you for a proper clinical orientation about the subject of cancer. So cancer is represented by this crab. So just like crab-like spreading. So the basis, the spatial relationship between two strands of DNA. They create major groove and minor groove. Major groove is a wider groove, you know pretty well about the structure of DNA, and the minor groove is a narrow groove. So these major groove and minor groove provide access for the binding of regulatory protein to their recognition sequences along the DNA chain. So these grooves are the correct pathways where the binding of regulatory protein takes place. So the recognition sequences will run through the DNA chain. So anti-cancer drug, bactinomycin, otherwise known as actinomycin D, exert cytotoxic effect by intercalating into the narrow groove of DNA double helix and interferes with DNA and RNA synthesis. So when we come across certain anti-cancer drugs prescribed by an oncologist to one of your relatives, then you should be knowing how it works. The biochemical basis of that particular anti-cancer drug, how it works, should be known to you so that you can explain to your relatives, and they will be very happy and they will be satisfied by your knowledge. So the knowledge attained by you should be useful to your people at least. That is the first stage of your application. Then at a later date, when you become a specialist, oncologist, you can you can delve deep into the subject, and widely you will be accepted by the people. So anti-cancer drug actinomycin, that's otherwise known as actinomycin D, exert the cytotoxic effect by intercalating into the narrow groove of the DNA double helix and interferes with DNA and RNA synthesis also. Anti-cancer drug camptothecin, it targets human type 1 topoisomerases. Etoposide targets human type 2 topoisomerase. So these are the various anti-cancer drugs, and they are targeting the sites, and by which they will act as anti-cancer drugs. Bacterial DNA diarrhea is a unique target of group of antimicrobial agents. They are called as fluorophenolines. Ciprofloxacin is one example. Telomerase, they are otherwise known as mitotic clocks. So their length is inversely related to the number of times the cell have divided. So if the length is short, the cell is divided number of times. If the length is too big, the cell is active and divided number of times. So the study of telomeres provides insight into the biology of normal aging, diseases of premature aging like progeria and cancer. So the study of telomeres, it opened an insight to the biology of normal aging, diseases of premature aging, otherwise we call it as progeria, and cancer. A small child will be there, but the face appears as if he is an old boy. So that's known as premature aging or progeria. Here you can see the pictures. We have seen one cinema also. Amitabh Bachchan appears as a small boy, and a small boy act like an old man. So this is typical example of progeria. So maybe they are very small of age, but their face appears as if they are of advanced age. So we are seeing in both sexes, the small boys or girls appearing as if they are of advanced age. So nucleoside analogs have modified sugar portion. Removal of hydroxyl group from 3' carbon of deoxyribose, then dideoxyadenosine, DDI, which is otherwise known as diadenosine, that prevents further chain elongation. So if you remove one hydroxyl group from 3' carbon of this diadenosine, further chain elongation is stopped. Conversion of deoxyribose to another sugar like arabinose, that will prevent further chain elongation. So how we can prevent further chain elongation? These are all the various methods by which we can prevent the further chain elongation. So these compounds block DNA replication and slow the division of rapidly growing cells and viruses. So this is what we want to prevent the cancers to progress. Cytosine arabinoside, cytarabine or ARA-C, it's used as an anti-cancer drug while we are giving chemotherapy. Adenine arabinoside, vidarabine or ARA-A, is an antiviral agent. So substitution of the sugar moiety is seen in azithromycin, AZT or zidovudine. So zidovudine, you know pretty well, is an anti you can come across this in the treatment of AIDS, zidovudine, nanobudine, all these things. So zidovudine, substitution of the sugar moiety is seen in azithromycin or zidovudine, and this can terminate the DNA chain elongation. All these drugs are generally supplied as nucleosides, and these nucleosides will be converted to nucleotides by cellular kinases. Remember, this is the strategic point where the nucleosides supplied will be converted into nucleotides by the action of cellular kinases. In spite of elaborate proofreading systems are there during DNA synthesis, at every step there is proofreading. If anything goes wrong, immediately it will be getting corrected. But in spite of all these elaborate proofreading systems during DNA synthesis, errors will creep into unknowingly. So these errors are like incorrect base pairing or insertion of one to few extra nucleotides. These are the things which usually go wrong. So DNA is constantly being subjected to environmental insults, and this causes alteration or removal of nucleotide bases. This is most important. So damaging agents like chemicals, nitrous acid. That's why this nitrous acid will be there when there are so many lightning thunders, and when raining is there, and these rains will carry the nitrous acid, and the people who drench themselves for fun or unexpectedly can't help themselves, so such people will be drained into will be drenched by this water rich in nitrous acid, and this nitrous acid can deaminate the bases. So this is one damaging agent. That's why when thunderstorms are there, people do not allow anybody to go out of the house. Especially more so, the girls of the house should not go into the nitrous acid range. And it will unnecessarily damage the DNA, it deaminate the bases. So remember, even though the boys they'll come out of the house um, cancelling the warnings given by the grand old parents or parents in the house. The girls will never come out of the house during thunderstorms. So remember, nitrous acid can deaminate the bases. So damaging agent. Radiation, non-ionizing UV radiations can fuse two pyrimidines adjacent to each other in the DNA. High energy ionizing radiations can cause double strand breaks. Bases are altered or lost spontaneously from mammalian DNA at the rate of many thousands per cell per day. So these are lost. Nobody can prevent it. We have to accept that this is a common general loss. If this damage is not repaired, mutations is introduced. And when the mutation is introduced, that leads to loss of control or the proliferation of mutated cells. And that will lead to cancer. So this is the fundamental method by which you have to understand the biochemical basis of cancer. So luckily, our cells are remarkably efficient at repairing the damage done to the DNA. The repairing system involves recognition of the damage. So wherever the damage is there, lesion we call it, it should be recognized. So on which part of the DNA the damage took place. Removal or excision of damage is another one. Replacement or filling the gap left by the damage, that's another one. Excision of that damaged portion using a sister strand as a template for DNA synthesis and ligation. So this can affect 1 to 10s of nucleotides. So you can lose 1 or 10 of the nucleotides by excising and then ligating the normal healthy strands, sister strands. The repair synthesis of DNA can occur outside the S phase of the cell cycle. This is what you have to remember when this question is asked in your Viva. So repair synthesis of DNA can occur outside the S phase of cell cycle. Mismatch repair, we abbreviate this generally as MMR. So mismatch repair is known as MMR. So sometimes the replication errors escape the proofreading activity during DNA synthesis. And this causes mismatch of 1 to several bases. MMR is mediated by a group of homologous proteins. And the example of such homologous proteins are known as mute proteins. MMR occurs within minutes of replication and reduces the error rate of replication from 1 in 10 to the power of 7 to 1 in 10 to the power of 9 nucleotides. So very fast. This will enact very fast, and it will within minutes of replication to reduce the error rate of replication from 1 in 10 to the power of 7 to 1 in 10 to the power of 9. Mutations to the proteins involved in MMR is associated with hereditary non-polyposis colorectal cancer, HNPCC. It's known as Lynch syndrome. You have to remember this whenever you become a great oncologist or a clinical specialist. Then you should remember most of the times the cases of colorectal cancers will come known as Lynch syndrome. Especially this will run in the families. Suppose you come across one patient, say a man of more than 70, 75 years or 80 years of age, with the broadening of the abdomen, distension of the abdomen, causing a lot of distress, and defecation will be a problem for him. He cannot take anything and he cannot digest anything. So life will be miserable for him. And he cannot clearly explain what is the problem with him. And we have to understand. So most probably that fellow may be having a colorectal cancer, otherwise known as Lynch syndrome, that runs in the families. hereditary non-polyposis colorectal cancer. So HNPCC confers an increased risk of developing colon cancers up to 5%. Not only colon cancers, other type of cancers also may be scapegoated for that fellow. Pyrimidine dimers can be formed in the skin cells of humans when they are exposed to unfiltered sunlight, having a lot of UV radiation. So when the school persons are working in the hot light, hot sunlight, so they will be exposed to this unfiltered sunlight. They are working for the sake of their family. They should make the both ends meet, and they should go home with some money. So the children and other family members may be properly taken care of. So the pyrimidine dimers can be formed in the skin cells of humans when they got exposed to unfiltered sunlight. And this unfiltered sunlight, they have a lot of UV radiation, ultraviolet radiation. All said and done, and ultraviolet radiation is there even in this bar light or tube light, under which we will sit in the classrooms or libraries. So it's unavoidable. But unfiltered, strong sunlight, that is the most dangerous one. And the skin cells will form pyrimidine dimers. So colorectal cancer, this is the example. You can see the descending colon, transverse colon, descending colon, and rectosigmoid. So in the descending colon, sometimes the tumor may be developing. And even in the ascending colon also, the tumor may be developing. So wherever the tumor is there, we got the problem. And the multiple polyposis is another example here. So this runs in the families. And just without running in the families, most probably nothing can happen, but we do not know the family history. We may be knowing mostly about our family of father, grandfather. That's all. Beyond that, we do not know who suffered what type of disease. So maybe our father may be knowing about the grandfather. That's all. And to give the details of all this, they should be living. It's impossible. They cannot live up to that age. So nobody can give the positive history that runs in the families. But the colorectal cancers are still more common in such conditions where we forget. So in the rare genetic disease, xeroderma pigmentosum, XP, that is the abbreviation given for xeroderma pigmentosum. The cells cannot repair the damaged DNA. So that results in extensive accumulation of mutations, and consequently, early and numerous skin cancers can affect that child. So XP, xeroderma pigmentosum, can be caused by defects in any of the several genes that code for XP proteins. They are required for the nucleotide excision repair. So NER is nucleotide excision repair. So in order to repair, we need nucleotide excision repair. And for that, we need large number of XP proteins. And XP can be caused by defects in any of the several genes that code for the XP proteins required for nucleotide excision repair. So these are all the things that you should definitely remember throughout your life. So this is how a normal photograph of a girl. So that beautiful photograph, the face was disfigured by xeroderma pigmentosum. You see, it's highly impossible to think about this face when we are seeing the original photograph taken in the childhood days. Quite pathetic, isn't it? We can't help it also. Xeroderma pigmentosum. So double strand break repair ionizing radiations, chemotherapeutic agents like doxorubicin, and oxidative free radicals, they all can cause double strand breaks in DNA. So these double strand breaks will be lethal. That can be repaired by two systems. So you can see the mitochondria activating drugs, the cardiomyocytes, they cause cell deaths and cardiotoxicity, and the cancer cells, they cause the cell death and the cancer regulation. So doxorubicin, upregulation of DRS, TNFR1 and FAS and DR5. So the circulating death ligands, TNF alpha and FASL and trail. So cardiomyocytes will be affected and lead to apoptosis, and tissue damage will take place that lead to cardiotoxicity. So it's not only the cancer, but the repercussions of the cancer may lead to this type of cell damage and cell death. So NHEJ, non-homologous end joining, in which a group of protein mediates recognition, processing, and ligation of the ends of two DNA fragments. Some DNA are lost in the process, and consequently NHEJ error prone and mutagenic things will happen. Defects in NHEJ are associated with the predisposition to cancer and immunodeficiency syndromes in AIDS. So second repair system is homologous recombination, HR, using enzymes that normally perform genetic recombination between homologous chromosomes during meiosis. HR system is less error prone than NHEJ. HR occurs in late S and G2 phase of cell cycle, but NHEJ can occur at any time in the cell replication. Mutation to the proteins like BRCA1 or BRCA2 that is causing the breast cancer 1 or 2, they are involved in HR. It increases the risk for developing breast and ovarian cancer. So these are the things you should remember. Which type of mutation lead to which type of cancer. And if you know this, you'll be able to explain it to the patients, whether they are close relatives or just patients. So anywhere, they need one consoling voice, and that consoling voice should be well knowledgeable in basics. And this is the basic knowledge in biochemistry that will empower you to explain anything in cancer. So now we will go into the subject proper. So the theory of oncogenes was foreshadowed by German biologist Theodor Boveri in his 1914 book. That book name is Concerning the Origin of Malignant Tumors. So in that book, he predicted the existence of oncogenes that become amplified during tumor development. So he wrote that there may be oncogenes existing, and slowly on a gradual time period, they will be amplified and lead to a tumor development. So later, oncogene term was discovered in 1969 by National Cancer Institute scientists George Todaro and Robert Hibner. And at this juncture, we should remember the two people, Bishop and Warnes. So Bishop was very happy man, and Warnes was still more happy. Instrumental music. He likes instrumental music. He plays the piano and gets the solution for anything. That's the way of thinking. Sometimes we will be singing some song repeatedly while we are reading a book. And that's a favorite habit for some people, isn't it? So we should know these are not only the pastime for us. Class lo nanu araganta. So these are not the pastime for us, but sometimes they may be uh, a real solution for us. So Bishop and Varnas, if you read out their biography, you'll be finding wonderful habits for them, and these habits together they worked up, and finally it led them to get the Nobel Prize in Physiology and Medicine in 1989. So they discovered the cellular origin of retroviral oncogenes. So this is what we should be knowing about the history. This type of positive histories will definitely give you a good example of how to come out in the life. So these are the great people, J. Bishop, Michael Bishop, and Harold E. Barnes. You see their faces, how nicely they are contented in their life. Oncogenes were first discovered on cancer-causing viruses, but they also are found in all normal cells. So in original unmutated wild-type allele of an oncogene is known strictly as a proto-oncogene. And mutations in the genes that control cell division are potentially very dangerous. And these mutant versions are cancer-causing oncogenes. So these are the 3 points which you should definitely have good idea. So DNA will be there and proto-oncogene will be there, and there will be a mutation taking place in that oncogene, and with that there will be deregulation of cell division. So this is the starting of the proto-oncogene converted into by mutation into an oncogene, and then deregulated cell division takes place. So the effects of oncogenes. Oncogenes in humans and other animals have the capacity to transform normal cells into malignant ones. Remember this one. This is the thing which we should be stressed by all of us. Oncogenes in humans and other animals, they have the capacity to transform normal cells into malignant ones. So these genes acquired at conception or mutated during life. So we will be acquiring these genes at the time of the conception, or later on there will be some mutation undergoing during life. And this makes the patient susceptible to cancer by altering or impairing several of the processes. So production of nuclear transcription factor that control growth. So that will lead to the MIC oncogene. So remember which type of oncogene is known to cause which type of damage. So MIC, MYC. Signal transduction within the cells is caused by RAS oncogene. And interaction of growth factors and their receptors will be exemplified by HER and NEU oncogenes. So these are set of oncogenes that you should know definitely, so that you know which type of cancers will result from this type of oncogenes. So more than 100 different oncogenes are identified. Identification is okay, but they finally established that only some have a good association exclusively with human cancers. So even though all said and done, there are 100 different oncogenes identified, but definitely only some will have association with the human cancers. So mutations convert proto-oncogene to oncogenes by amplification, translocation, and point mutation. These are the things ultimately you should remember. So mutations will convert the proto-oncogene to oncogenes by amplification, translocation, and point mutation. You know pretty well the meaning of all this in your intermediate level of education itself. Oncogenes are typically genes that encode growth factors or growth factor receptors. Downstream effectors of signal transduction pathways and enzymes responsible for the metabolism of activating proteins. So these are the things, the oncogenes, they are the typical genes that encode number one, growth factors, number two, growth factor receptors, number three, downstream effectors of signal transduction pathways, and enzymes responsible for the metabolism of activating proteins. So these are all the places where they effectively exercise their power. So classification. So there are several systems of classifying oncogenes, but there is not yet a widely accepted standard. We could not arrive at even till today. So they are sometimes grouped both spatially. Spatially means moving from outside the cell inwards, and chronologically, that is paralleling the normal process of signal transduction. There are several categories that are commonly used. Some of them, some of the examples are growth factors. Growth factors or mitogens are exemplified by C, cis. And the cancers associated with these growth factors or mitogens, exemplified by C, cis, and many others, are glioblastomas, fibrosarcomas, osteosarcomas, breast carcinomas, and melanomas. So gene function induces cell proliferation. So that's the gene function. So you know pretty well about the glioblastomas for central nervous system. When you become a neurologist or neurosurgical specialist, you'll be coming across all these cancers of glioblastomas. And you know pretty well about the fibrosarcomas in breast. Fibroadenomas will lead to fibroadenoma sarcomas or fibroadenomas. Osteosarcomas, so connected with the bone and other soft tissues around the bone, and breast cancers, and melanomas in the skin. So color producing moles. So they will turn out finally into melanomas. When they are enlarging, when you observe that the moles are getting enlarged, then you have to suspect that they are going into melanomas. So remember, growth factors or mitogens, exemplified by CCs, they lead into glioblastomas, fibrosarcomas, osteosarcomas, breast carcinomas, and melanomas. And gene function induces cell proliferation. And the other category is cytoplasmic tyrosine kinases. So SRC family, SYK, ZAP70 family, and BTK family of tyrosine kinases. So these are the three tyrosine kinase families. So ABL gene in CML, that is Philadelphia chromosome. So they lead to colorectal and breast cancers, melanomas, ovarian cancers, gastric cancers, head and neck cancers, pancreatic cancers, lung cancers, brain cancers, and blood cancers. What not? A big jumble of all the tangling cancers will be there. So they mediate the responses to and the activation receptors of cell proliferation, migration, differentiation, and survival. So these are all the things they are causing colorectal cancers, breast cancers, melanomas. You know pretty well the breast cancers are quite amenable for chemotherapies and radiotherapies, whereas colorectal cancers, if they are poorly differentiated, nothing can be done. So for example, we have the multiple polyposis turning into colorectal cancers that will run in the families. So these are all the things where difficulty arises. So all are not amenable for chemotherapy or radiotherapy. But when an obstruction is going to take place, definitely we have to do dissection and we have to do end-to-end anastomosis. Suppose a colorectal cancer takes place, we have to do colectomy. So colon, 50% of the colon can be removed, and then end-to-end anastomosis will take place, and we are not sure whether no recurrence or recurrence. So within 1 year, there will be recurrence at the anastomotic site, leading to again obstruction. And what we have to do, we have to again do the colonoscopy, and we have to take a biopsy from that and from that proliferating growth, and we have to get the histopathological report, and the histopathological report says that it's a recurrence. Then nothing can be done, isn't it? So these are all the problems. Nothing cannot be done. Something can be done if the patient accepts it. But that's something, again, we have to open up the abdomen and we have to do the resection. Far beyond the segment involving the growth. And then we have to do end-to-end anastomosis and we have to see what happens. So before that, we have to do at least 2 or 3 cycles of chemotherapy. And this chemotherapy at least will suppress the actively proliferating cancer cells, so that by the time we clamp and cut the area, there may not be spread. They say like that, but I have never seen with my own eyes. Again, it will recur even after 6 months or 1 year. So there is only a 30% chance of survival for 5 years when we do the colectomy for the first instance. So second year, again, recurrence will come. Third year, again, recurrence may come. Even before 1 year, 6 months, recurrence may come. As long as the patient is having money to afford, and as long as the people around him take care of him, to take him to gastroenterology institutions of reputation in our country, then we can have a treatment. But if nobody is there in villages, they will go into obstruction and slowly they will die with a slow death, a miserable death, isn't it? So remember, regulatory GT bases. These are exemplified by RAS proteins, adenocarcinoma of pancreas and colon. Adenocarcinomas are quite amenable for chemotherapy and radiotherapy. If it is poorly differentiated, nothing can be done. Adenocarcinomas, something can be done. So RAS protein is the example for regulatory GT bases. Adenocarcinomas of the pancreas and colon and thyroid tumors and myeloid leukemias. So they involve in the signaling, a major pathway leading to cell proliferation. And along with these oncogenes, we should know something about tumor suppressor genes. A tumor suppressor gene or anti-oncogene is a gene that regulates a cell during cell division and replication. This is the definition. All of you should keep it on your tongue throughout your life. That is our duty. We should be able to hear what all the patient tells. We should be able to convince the patient to receive what all the treatment that we are going to give. And we should be able to interpret the problems or benefits of our treatment, and subsequently what the patient may have to face in his life. So for all these things, you should know the fundamentals, the definitions as it is. You should never modify these fundamental definitions. Tumor suppressor gene or anti-oncogene is a gene that regulates a cell during cell division and replication. So if the cell grows uncontrollably, it will result in cancer. So when a tumor suppressor gene is mutated, it results in a loss or reduction in its function. A total loss of the function may be there, or a part of the function may be reduced. So in combination with other genetic mutations, this could allow the cell to grow abnormally. Not alone, these things will lead to the abnormal growth. In association with other mutations or other genetic mutations, they will allow the cell to grow abnormally. The loss of function for these genes may be even more significant in the development of human cancers. So remember, loss of function is the main thing. The combination of other genetic mutations and all are secondary. They may be there or may not be there. So loss of function for these genes may be more significant in the development of human cancers compared to the activation of oncogene. So this is the pictorial representation. So external signal molecule, it will give a signal to the dividing receptor, and then receptor will give signal to divide, and then signal transmission protein will receive it, and the tumor suppressor protein will carry it, and signal will be conveyed to the cell, and transcription factors, they will be acting in the DNA. So this is the normal one where the external signal block the things, then nothing will be continuing. So cancer-associated genes are functionally classified into three categories. Genes that induce cellular proliferation, tumor suppressor genes, inhibitors of cellular proliferation, and genes that regulate programmed cell death. So these are the three types functionally classified. So cancer-associated genes are functionally classified into three categories. Number one is genes that induce cellular proliferation. Number two, tumor suppressor genes that are inhibitors of cellular proliferation. Number three, genes that regulate programmed cell death. Inactivation of these suppressor genes results in the unregulated proliferation. Every sentence you have to just lock it up in your brain. Otherwise, it will be very difficult for you to explain the things to the patient in future. Many of the tumor suppressors, they work to regulate the cycle at specific checkpoints in order to prevent damaged cells from replicating. There are many checkpoints, and at all the checkpoints, they should be able to interfere. So tumor suppressor genes can be grouped into caretaker genes, gatekeeper genes, and landscaper genes. So these are the simple colloquial terms into which the tumor suppressor genes are grouped. So the first one is caretaker gene, other one is gatekeeper gene, and more recently another group, landscaper gene. So caretaker gene, as the name implies, ensures stability of the genome via DNA repair, and subsequently when mutated, allow mutations to accumulate. So when the caretaker genes are mutated, then only the mutations will be allowed, and these mutations will be accumulated. So this is the first step where we are knocking off the caretaker genes in many of the cancers. So remember clearly what is going to happen in cancers. Caretaker genes ensure stability of the genome via DNA repair, and subsequently when mutated, allow the mutations to accumulate. So gatekeeper genes directly regulate the cell growth by either inhibiting the cell cycle progression or inducing apoptosis. When something is unrequired, then apoptosis, it leads to apoptosis, cell death. There ends the business, isn't it? So when a small congenital malformation is there, if the congenital malformation is a smaller one, and if the child can survive lifetime with that, no problem will be there. If it is not compatible with life, then natural abortion. Survival of the fittest will remain, and non-survival of the useless one will be aborted. So the gatekeeper genes directly regulate the cell growth by either inhibiting the cell cycle progression or inducing the apoptosis. Landscaper genes, this is the modern one, they regulate the growth by contributing to the surrounding environment. When mutated, can cause an environment that promotes unregulated proliferation. So landscape. So entirely, they just don't want to take care of their own house. The entire landscape should be taken care of. So the landscape of genes regulate the growth by contributing to the surrounding environment. When mutated, can cause an environment that promotes unregulated proliferation. So tumor suppressor genes are more precisely the proteins. So there are so many proteins produced by these genes. That's why, more precisely, we call them as proteins for which they encode. They have a repressive effect on the regulation of the cell cycle, and they promote the apoptosis, or sometimes both. That's the last division. Tumor suppressor proteins function in various ways, and these ways by which the work of tumor suppressor proteins is number one, repression of genes that are essential for continuing the progression of the cell cycle. If these genes are not expressed, the cell cycle doesn't continue and effectively inhibiting the cell division. So coupling of the cell cycle to DNA damage. As long as there is a normal DNA in the cell, it will not, should not divide. If the damage can be repaired, cell cycle will continue. If the damage is not repaired, the cycle should not be allowed to continue. So third one is apoptosis. If damage cannot be repaired, the cell should be initiating the apoptosis. If we have sprinkled some organophosphorus compound to cut short the infection to the plants, if nothing took place, what we have to do? We have to cut away the branches. At least the new branches will come out with new leaves, and the growth of the tree will take place, isn't it? So apoptosis is, if damage cannot be repaired, the cell should initiate apoptosis. That is programmed cell death to remove the threat it poses to the organism as a whole. So instead of entire organism getting wasted, a small cut, that is apoptosis of that particular area of cells, will be curative. Then cell adhesion. So some proteins involved in cell adhesion prevent the tumor cells from dispersing. So when when the cells are adhesive, there will not be a spread. So the tumor cells cannot be dispersed by the cell adhesion. So they will block the loss of contact inhibition and inhibit metastasis. So the tumor cells will not be moving out from one place to another, that is metastasis. So they will slowly inhibit metastasis. So these proteins are known as metastasis suppressors. So everything is not Greek and Latin. Everything got its own meaning. So in colloquial terms, these headings were created to make everything easy for the beginners in biochemistry like you to understand the wide range of subject. So DNA repair caretaker genes encode proteins that function in repairing mutations in the genome, preventing cells from replicating with mutations. So with mutations, the cells should not be allowed to replicate. What will happen? Only the mutated cells will come out of replication. That's not required. That should be avoidable. So DNA repair caretaker genes encode proteins that function in repairing mutations in the genome, and that will prevent the cells from replicating with mutations. Furthermore, increased mutation rate from decreased DNA repair leads to increased activation of other tumor suppressors and activation of oncogenes. So remember all this. This is how you have to build up your knowledge. So examples: retinoblastoma protein, RB protein, PRB protein. PRB was first tumor suppressor protein discovered in human retinoblastoma. Specifically, PRB prevents the cell cycle progression from G1 phase into S phase by binding to E2F. and repressing the necessary gene transcription. So this prevents the cell from replicating its DNA if there is damage. P53, that is TP53, is a caretaker gene. We read about it repeatedly in our previous classes. So this is most important one that will come quite commonly in short notes or other short notes. P53 or TP53 is a caretaker gene. It encodes the protein P53, which is nicknamed as the guardian of the genome. So these are the three things that you should definitely write when an outer short notes is given. And P53 has many different functions in the cell, including DNA repair, inducing apoptosis, transcription, and regulating the cell cycle. So these are all the things that you should. This is not the end of the subject. It will be continuing when you go into the Department of Pathology in your second year of study of MBBS. So that you continue there. And you should remember these things, and quite happily you should be telling that in the class so that your lecturer or professor will be very happy of your knowledge related to basics of biochemistry. So P53 has many different functions in the cell, including DNA repair, inducing apoptosis, transcription, and regulating the cell cycle. So BCL2 is a family of proteins that are involved in either inducing or inhibiting apoptosis on both sides. The main function is involved in maintaining the composition of mitochondrial membrane and preventing cytochrome C release into the cytosol. The cytochrome C release into cytosol will also cause damage. When cytochrome C is released from the mitochondria, it starts signaling the cascade to begin apoptosis. So SV1 and SNF. So these are the chromatin remodeling complex, which is lost in about 20% of tumors. So chromatin remodeling complexes SW1 and SNF. So these are the chromatin remodeling complexes. They are lost in about 20% of the tumors. So these two chromatin remodeling complexes, they got the ability to move nucleosomes, which condense the DNA and allow for transcription or block transcription from occurring for certain of the genes. So RB1 gene is a tumor suppressor gene, and retinoblastoma can result from the mutation of RB1 gene. And proto-oncogene are present as in healthy human cells also. So a normal cell can be transformed into a cancer cell by ionizing radiations, mutagenic chemicals, oncogenic bacteria. All of these things will come together to convert a normal cell into a cancer cell. Tumor suppressor genes are sometimes called as anti-oncogenes. We got tumor markers for all these things. We will be learning about this in the next class. At, another 9 days afterwards. So retinoblastoma gene is a anti-oncogene. We got one wonderful book, Genetics and Genetic Engineering, by one great lady, Lisa Yount, Lisayount. So this is a very good book. Every one of you can read this book to get very good inspiration of the great scientist. So cancer is the second most common cause of death in advanced countries also. So the modifiable risk factors are: number one, tobacco. 30% of the cells, 30% of all the cancers, they are due to tobacco smoking. At least 15 cancers are linked to this. So by 18th year, 80% of the people may unnecessarily develop this at a small age. So they start smoking it right from the childhood. They will be unnecessarily losing their life by 18th year. So leave alone the people who are chain smokers. Nothing can be done to prevent their death, isn't it? So more intense counseling is needed for them, and all of you should try to reinstate nicotine replacement therapy with the patches, nicotinell, or the gum, or lozenges, or medicines like bupropion, or varenicline, or government should formulate local laws. If somebody is found smoking, some stringent punishment should be applied by the government. And especially when somebody is pregnant in the house, nobody should smoke inside the house. So passive smoking will induce cancers at least 5 times more than the other normal people. So nutrition and physical activity should be, we can have the control over nutrition and physical activity. So we should avoid tobacco, we should be physically active, and we should maintain healthy weight. There should not be abnormal weight gain. We should consume diet containing fruits, vegetables, and whole grains. And we should lower the consumption of saturated or trans fatty acids. So saturated fatty acids will directly add to the problem of heterogeneity. And trans fatty acids, pretty well, we also ultimately get converted into heterogenic cholesterols. So you should limit the alcohols, and you should avoid the excess sun exposure. In yesterday's class on folic acid, gave a very good description about the alcohol and other things in causing cancers. Radiation from radiographic studies. So you have to choose wisely the diagnostic CTs. So diagnostic CTs will escape, they will allow us to escape from the radiation from radiographic studies. So we need not just sit by the radiographic studies. So there are 10 most common cancers, and in males and females, the incidence is different. The prostate cancer is present only in males, that occupies 27%. The lung and I think finish. The lung and bronchial cancers 14%. Colon and rectal cancers 8%. Urinary bladder 7%. The colorectal cancers, signet ring cancers, very dangerous. They are brutally differentiated. Nothing can be done for them. Remember, signet ring cancers. That is colorectal cancers. Signet ring. Remember that word. You see that description in histopathological studies, and you have to say nothing is left for the patient. Only you have to go on doing the end-to-end anastomosis, resection, end-to-end anastomosis, chemotherapy, 2-3 cycles, preoperatively and post-operatively. That too, patient should be able to tolerate that, provided the repeated blood transfusions, isn't it? So urinary bladder cancers are 7%, melanomas 5%, lymphomas 5%, kidney and renal pelvis cancers 0.05%, oral cavity and pharyngeal cancers 0.04%, leukemias 4%, liver and intrahepatic bladder cancers, gallbladder cancers 3%, other sites 18%. When that is coming for the females, the women will have breast cancer incidence 29%, and the lung and bronchus 13%. So the breast cancers are increasing because most of the people now they are opting for not getting married and not getting children and not giving breastfeeding to the children. So when something is prevented in normal life, it is going against the will of the cell, isn't it? So that will unnecessarily cause breast cancer. So breast cancer is 29% highest in females in all the other cancers. Of course, also have been done. Chemotherapy and radiotherapy are quite available, and if you scrupulously follow this, they can have a normal life for at least 9 years to 10 years. So lung and bronchial carcinomas 13%, because most of them will be staying inside the kitchen for most of the time. They may be having increased incidence of lung cancer or bronchial cancer. Colon and rectal cancers are 0.08% only, because they will hardly eat nothing. No deep fried foods, no fried chicken, fried fish. Nothing will be left for them by the time they sit for their food. Most of them will be consumed by the head of the family and the male children in the house. That is one blessing in disguise to the females. So they don't have the colon cancers that frequently as suffered by the men folk in the house. So uterine cancers are 0.06, thyroid cancers are 0.06, lymphomas are 0.05, melanomas are 0.04, kidney and renal 0.03, and pancreatic cancer 0.03, leukemia 0.03, and other sites are 20%. So uterine cancers, hormone therapy is usually given, like progesterone and tamoxifen and aromatase inhibitors are given. And combination chemotherapy, cisplatin, hydroxyribosin, and docetaxel, and carboplatin. Ovarian cancers, combination therapy, paclitaxel and carboplatin. Cervical cancers, along with radiation, we have to use cisplatin, and combination chemotherapy, cisplatin, paclitaxel, and okay, done. Chala satisfied.